Alright, DraftScience video. Yeah, it's radiation. I think we'll talk a little bit about just did some researching and such, and it all is very quite consistent with what my theory argues is taking place. So I just thought I'd go through a little quick explanation. You know, it's what I've learned. Some of this stuff you know, and some of this stuff is add-on. But anyway, so the stuff that decays, the stuff that's radioactive, is usually the big atoms. And the key thing that happens in atoms is that some of them acquire more neutrons than they have protons. So you can sort of imagine that if neutrons were like magnets, and they were sticking with stuff at either end, it would be like there would be an extra 2 magnets because they needed more distance between something. So it's like you needed more magnets to make this little infrastructure to be able to maintain a nucleus. And so that's one way of imagining it. Who knows the truth, but I'm just saying it's something like that. You need more neutrons to hold the protons together because there's so many of them. Their desire to their discomfort with each other is too extreme, and they need to spread out more, but they still need to be connected to the nucleus, blah blah blah. So anyway, these are the stuff that decays, generally speaking, or can be radioactive, or can cause radioactivity in the sense of emit stuff, fall apart, however you want to say it. Alright, so when one of these things is decaying, what's happening is it's basically turning into a different element. So it's going from a bigger nucleus to a smaller nucleus, or else in circumstances where there's heat and pressure, it's forcing 2 smaller elements together to make one of these bigger ones. But the more common case, I would suspect, is the fact that you already have the big one made and it just slowly starts to decay into a simpler element, a smaller nucleus. And so alpha particles are the ones that are released in that process. Basically, they're just an ejection of a hydrogen nucleus, so it's just 2 protons and 2 neutrons. And they're ejected at a speed, and the speed is what makes it a little bit interesting. So I guess you don't need a real picture for that, but I mean, so it's just the idea of these 4 things is what an alpha particle is, and then beta is the radiation that's really just electrons. They're just electrons with momentum moving, and electrons don't really like they won't maintain velocity. So what they're always doing is decelerating. So from the minute they're ejected, almost, they're starting to decelerate. They're slowing down. So this is consistent with my theory in the sense that you can imagine that if an electron was compressed into another electron, very close compression, that the force between them would become very strong, and that anything that released that pressure, the pressure that pushed them together, they would rebound at a high speed, because it's basically this argument that the force between them is relaxed, and then as you push it together, it's a lot more impacts. And the key thing is the impacts become almost having the same frequency. That is the impacts are almost a complete push, a very high acceleration. And so that's what beta particles are. They're just basically electrons. Now you have the alpha, beta, and then you have the gamma radiation. And the gamma is just the photon stuff. That's just this force stuff when it's released. So you can be in the form of X-rays or visible light, or any one of the electromagnetic spectrum, really, of this loose stuff. And so that's what's the gamma part. And so that's pretty much the range. So when it leaves as a ton, it's the gamma stuff. When it leaves as an electron, it's beta. And when it leaves as a piece of the nucleus, neutrons and protons, it's called an alpha particle. And like I said, all this stuff demonstrates that it doesn't really like to have acceleration. Now the exception would be the hydrogen nucleus, which can, if it's rotating, let's say if it's rotating on an axis like this, where three things are close together, one thing far, then you could theorize that the force in between these elements is stronger on this side than it is going this way. So it's moving, as it circles, it's moving more stuff one way than it moves the other way. So I don't know exactly how to configure that into a square, but it would be the appropriate triangle or something, where you'd have an imbalance on one side versus the movement at the other side. So this thing would swing down, these things would swing up, and they'd always swing up more than they would swing down. And so over time, that would end up being a velocity. So an alpha particle can have a permanent velocity. Now, they say that cosmic rays are a mixture of these things. Some 12% are being these alpha particles, which are rather large. So I have some doubt that in empty space the percentages are that high, but whatever. You know, I think some of it is just the radiation that's local to the Earth. In terms of the cosmic rays come in and they eject these little nucleuses out of the numerous atoms that are likely floating about in our somewhat dirty solar system. So I think once you got out of there, the percentage of alpha particles would decrease. But whatever, doesn't really matter. Not critical to anything. So the key thing about the electrons with momentum is that they seem to just want to give them all different names. And so muons are basically just these electrons with momentum. And you know, the catch is they're still carrying their propelling force, let's say. So you could imagine that some of this force could still be connected in the sense that all the stuff going the same way as the particle could have different, it would take it time to catch up. So if the particle leaves fast, there could still be bits in here behind it that are still pushing along with it and are maintaining its velocity by maintaining its acceleration, is a way of saying it. It's still being slightly, there's a compensating acceleration going with their velocity, but it inevitably will run out. Now, I would argue that this stuff is what they call neutrinos. So neutrinos are basically them just receiving the which you'd almost call the gamma element of radiation that's with the electron. So the electron's carrying some electromagnetic radiation, some tons that are associated with it in the sense that they're still passing through it, and it hasn't finished its acceleration, you could almost argue. And once it starts decelerating, you know, then that whatever that was won't exist anymore, and the muon will go back to being an electron. Yeah, and yeah, so that was kind of simple. But that's really all this radiation stuff has to do with. I mean, the thing that's important is that the durability of the neutrons, the protons, and the electrons seems pretty clear. That they're quite durable. That they don't break into these quarks and all this other kind of stuff. They might be made of that stuff, but they don't break up into it, even in pretty extreme alchemy. You know, pretty extreme conversions from one element to another element, even in extreme environments. There's not a whole lot of destruction of a neutron, let's say, or a proton or an electron. So they are very durable, and the speed of their ejection is essentially the definition of what name they're given. But that's the constituents of radiation are really just these pieces. You're either emitting a big thing, a clump of nucleus, you're emitting an electron, or you're just emitting the regular photonic, quantonic, you know, a packet of the force, you know, of force, in a form that's not going to be visible. I mean, it might be in the form of a very high frequency or no frequency even form, but it's those little arrows, and a packet of them, a bunch of them in the same location. And again, I would argue that neutrinos are basically what they've defined as a clump, okay, of force. But it's just like gravity, you could call it. Neutrinos are just gravity. They're gravitons now, essentially. So yeah, it doesn't need all the complexity they've placed on it by using all of this kind of, strangled assignment of labels and names. Baryons are now electrons, and it just is just completely unnecessary to completely change the name of something that's fundamentally or elementally the same thing. And so this has something to do with charge, so that's another part of this. They they base a lot of this stuff on these name designations based on an association with a charge, but the charge isn't being measured in a normal environment. It's being measured based on when you have a highly accelerated electron, let's say. You're not going to get a true reading of its charge. You're going to get an inaccurate reading of its charge. So they're basically calling a slightly negative electron, which it might be called, less reactive to a magnetic field electron. Some other name, a muon or whatever it is, and it's not really fundamentally different. It's just that its velocity changes its reaction to the field, and also the tendency is, as I pointed out, is these things can lean in a direction, and so it may be completely arbitrary whether we call one thing or the other thing just based on the fact of where it initializes which direction it tends to have, or its spin, so to speak. And it can go in, before it starts to decelerate, and before it picks a side to spin into, it's the same thing. And it's only when the arbitrary decision of which force hits it first and decides which way it starts to lean, that it's the tendency of which way it's going to spin down or decelerate is decided. So it's not really any kind of, it's just a happenstance of what the odds are in the field it goes through. And even though there's lower odds that it might go left than right, some will go left. And we'll give them a different name. And they're really not different. They're just the same thing. They're just it's a different circumstance. So put the other thing in the same circumstance, it would behave the same way. So they're really the same thing. They're just circumstantially being called different because one's standing in water and one's not standing in water. Some kind of thing like that. Yeah, so that's probably enough. Yeah, I don't think I need to go through the other stuff I've already explained, but apparently I do, because nobody seems to understand. I mean, I think this is rather simple, and I think I've explained it in kind of a simple way, and there's just no evidence that people are catching on at all. Now, I mean, I get comments that are just like, the asymmetric topology of atoms may create the weak force of gravity. I've already pointed out where I think gravity is created by. I think gravity creates the weak forces and magnetism. Gravity isn't being created by something. Gravity is the elemental force. Gravity is the first force. The others are the secondary forces. A tiny attractive field. Again, it's not tiny, but again, this whole argument that the stuff that's moving galaxies around is a weak force is, in my opinion, substantially retarded. Water has its properties because of molecule shape. Water has its properties because of molecule shape. What does that even mean? I'm not a physicist, just speculating. Well, you're obviously not much of a pay-attentioner. Okay, I don't know. Like I said, I just don't understand how this comment, after these 400 videos I've made, is it all responsive to anything I've said? It's, there's a big field of energy that's going in all directions. Some of that energy is always pointed at every location in space. It's a pressure gradient. It's all pressure. And that same pressure goes all the way down to the individual atoms. They're in the same space we are in. The neutrons and the protons exist in the same exact space we exist in. And that pressure for them is quite personal. It's complete and real. That's why it's stronger. And by the time it gets out to us, in terms of the material function, it's having to do things like as I pointed out, this is really the stuff moving the speed of light. Now this movement is a lot slower than the speed of light, but that's because the little elements inside are moving the speed of light, and all the ones going the wrong way have to actually stop going the wrong way for a moment of time and go this way. And that's what the atoms are doing. They're spreading the force over millions or billions or trillions of other little arrows. And it's that spreading of the force that appears like weakness to us. But if you think about it, you know, it's a pretty powerful force if it can, you know, move all of this matter, stuff going this way and that way and that way and all the wrong ways, and force it to go forward. But yeah, I just don't, you know, I just don't get it. You know, and this guy's, well, I might as well do it now because I won't have to make a separate video about it, so might as well make this a semi-comment video too. He's still arguing about this relativity stuff, this mindless marbles guy. And, you know, it's just so irritating because, you know, I've tried to make it as simple as possible. And he just keeps arguing that he can have it both ways, that he can say, okay, you know, I mean, I've made it as clear as I can. I mean, you're going half the speed of light, and if you say, and, you know, and there's a hole perpendicular on the ship, and if you say the light goes through the hole, then you're basically saying the light is given momentum, that you can give light momentum, like a baseball on a train. When I throw it, I have to throw it behind the thing I want to hit, because the baseball is going to have the momentum of the train. And he's saying a photon of light does the same thing. So theoretically, if I was on this spaceship and I wanted to hit another target with my ray gun, I would have to aim at a 45-degree angle to hit him. If he was stationary, I would have to aim way, way behind him and shoot, my light ray would bend and then hit him. So he thinks that's reality. And I'm saying that's not reality. Light is supposed to be the thing not influenced by the emitter. That was Einstein's statement. It was a lot of people's statement. And this interpretation of relativity violates that. Now, Einstein's wrong. I mean, it's just this whole notion that nothing ever changes with velocity is just stupid. And they should never, I mean, it only works when you're going really slow. You know, when you can't measure the speed of light differences. When there's no ruler to make measurements. But when there is a ruler, and you're going fast enough to measure the differences, it doesn't work. It's stupid. Now you want to keep arguing that you can do it, okay, fine. You're saying you can bend light. I'm saying it's preposterous that you can give light more than one momentum. I'm saying it's nonsense. And I'm saying the minute you do it, you've theoretically made the light go faster than the speed of light. There's no other way to draw the hypotenuse. I said it already 14 times. So I'm done with this. If you bring it up again, I'm just going to block you. You say light photons can have 2 momentums or 3 momentums. I say that's a preposterous pile of nonsense. So shut the fuck up already. We fundamentally disagree. You think a force can be bent like that. I think it's just silly. There's no evidence of it anywhere, and all you have as evidence of it is the Edinburgh experiment, which never been successfully repeated, and a bunch of crappy lensing images that suck. And that's all you got is evidence that you can ever do this give light to momentum bullshit. And it's bullshit. I mean, Einstein was stupid to think of bending light with gravity, because he should have known the implication of that is I've given it two momentums. And it's a force. You can't give it two momentums. It's not a three-dimensional object. God, you people are just fucking, you're stone cold dead brained. Alright, so anyway, I'm done with it. You don't get it, you don't get it.